So I want to thank everybody for inviting me here today. I think the first thing to say is I'm an engineer, okay? And I am an engineer, and that's what I'm always going to be. I'm not a social scientist. I'm never going to be a social scientist. My social science skills amount to the fact that I have a wife and 2 daughters. That's it. And so my wife will explain to you what that means. So this is the very first slide I have, and the reason it's in here is because yesterday evening on the way, or yesterday morning on the way into Lisbon, I met this gentleman and his girlfriend on the plane. They were sitting beside me. The gentleman is a farmer from, so everybody knows where Ireland is. Is there a laser pointer in this? Oh, sorry. Is there a laser pointer?
Yes, there is. In the middle.
Yeah. So this gentleman here is a farmer in this region here, the actions in Northern Ireland. We won't go into the politics of it. We've had a political thing from the rector. I can speak about politics in our university as well. He lives in this region here, and speaking to me, he found out I was in the energy business, and of course he immediately started asking me about the proposed building of a transmission line here. Okay? Now as it turns out, the CEO of the company that's building that transmission line is my first ever graduate, and I got off the phone with him as I got onto the plane, and he was the first person to call me as I got off the plane. So I didn't enter into too much discussion with him. I think the important point is that energy impacts everyone in the world. He's a farmer, he likes renewable energy, but he's just a bit sort of, why are we building it? You know, he's genuine questions, real questions, okay? Very wrong person to answer them, an engineer, for sure, okay? And you'll see why in a minute. So this is the outline. I'm going to talk about low carbon energy systems, and I'm going to talk about the importance of a concept called energy systems integration, but that's the area I sort of come from. And I'll try and show you why the social science is important. I'll give you some examples, some observations, some initiatives, some conclusions. I think the most important thing is down here. I am an expert in some things, a very narrow area. I'm actually an expert in power system dynamics, okay? It's a very specialized field in electrical engineering, and not being disrespectful, but most people in here will never understand it. Like, I won't understand many of your specialities at all. So I'm a complete and absolute novice in many of these things, and if you want to criticize me, abuse me, work away, because then I might learn. Okay, but I'm never going to learn fully, as my wife will tell you. So, energy systems integration, what is it? I'm going to skip over this slide. It will be in a slide deck. If you want to read it, this is the formal definition, but I'll leave it at that. So this is the concept of energy systems integration. The first thing to say about this slide is that from your perspective, and I know that there was engineers, management, there's not only social scientists here, but from your perspective, this slide doesn't really include you. And it's not deliberate on my part, we're struggling to, we know that the social sciences is important, we're trying to include them in this initiative, but we're all engineers. So one of the things I'm here today for is to say, a bunch of us are doing this, and we'd like to welcome social scientists in to help us, etc., etc., etc. But the concept is, this is an energy system. These are the scales from the customer, and again, customer, citizen, consumer, the same to me, but you know the difference, I don't, okay? So we call it customer, city, so these are the different scales. These are the different energy vectors, electricity, carbon, fuels. These are not energy vectors, but water, data, and transport. Transport is another network that uses energy. Data is a huge enabling technology for the energy system. And water is an end use, but it's an incredibly important end use. And we think it's actually part of this concept, and I'll tell you why in a minute. So these are sort of engineering terms. We're trying to optimize this entire system across all scales and across all vectors. It's a big, huge optimization problem. Engineers love big, huge optimization problems, okay? But we want to do it to increase the reliability, increase the performance, minimize costs, and environmental impacts, okay? Yeah, I won't go into that one, that's not what I want to do. But the control variables, the things we're going to use to do it are technical, economic, and energy. Now again, we're getting close to social science there, but we're not quite there. Water, I'm just going to put this one slide up about water. Water is an enormous issue in the world. I'm sure from a social science point of view it's an enormous issue in the world. But this just gives you one slide. I use this with permission from General Electric. 47% of the global water reliant power production is in areas of water stress. So water, energy nexus is incredibly important, and there's obviously a social science or behaviour part. Okay, so to get to the sort of the technical areas and try to show why social science is important, examples of grid flexibility is social science perspective as seen by an engineer. My wife is a yoga teacher. Okay? Ideal, but very valuable. So, and again, I don't know if this is, but let me know. I'll try and get this across. So one of the things about the integration of renewables, bringing lots of wind and solar onto the system, is that there's a thing called, it's a phrase called flexibility. People are talking about we need a more flexible energy system in order to integrate renewables. Who's heard of that term before? Okay, good. Turn to your person beside you who didn't say yes and explain it, because I don't have the time. So what it is that in order to integrate renewables, they are weather dependent. The wind and the sun. Okay, the one good thing about the sun is it comes up in the day and goes down at night, right? So it's a little bit predictable. But wind is not. So the resource is there when it's there, and that's it. You've got to try and use it. The consequence of that is that if you look at a power system, and if you look at the demand, this profile here is the demand of a normal power system, right? It's actually a simulation by a colleague of mine called Michael Milligan Nenrel. I use multiple slides from lots of my colleagues, all with permission. You'll see them quoted at the bottom, okay? But, Michael, I think this is a simulation. I don't think it's real data. But if you try to meet supply-demand balance, okay, on a power system, right? In other words, the generation must meet this demand. If it doesn't, this is what happens. This is Italy, this is the blackout in 2003. If you do not meet the demand with the supply, effectively the system collapses and blacks out, okay? So maintaining supply-demand balance is very important. And in an electricity grid, this is not like sort of maintaining supply-demand balance if someone says, demand is outstripping supply, and it says, well, listen, we'll have a cup of coffee, we'll have the lunch, we'll deal with it after lunch. You have sometimes seconds, right? You certainly mightn't have any more than minutes to do anything about it. So supply-demand balance electricity system is not something that has to be maintained. It has to be maintained on an almost instantaneous basis, okay? So this is why it collapses. So if you don't maintain this supply-demand balance, you have a reliability problem. But in order to do it, this is now wind. Wind is effectively, it's not free. Its marginal cost is zero. Once you build it, it's free, but you have to build it. So while it's there, you should try and use it. So if you try and use it, what happens is this profile of supply of demand effectively becomes this profile, because this energy is free. And you can see that this profile is much more. It goes down further, it goes down faster. Ergo, they say we need a more flexible system, because some other part of the system must make up this supply-demand balance. Makes sense? And that's why the lady here, okay, that's actually, just to be clear, that is definitely not my wife, okay? I was going to say something, but I won't. You're not videoing this, are you?
I don't know, probably yes.
You must be careful.
So if anyone wants to extort large amounts of money out of me, find out who my wife is, send her this or that. Okay, this. I know that every other Sarah Darby. Hey, Sarah, you've seen this before. This is a very funny slide, but it's dead serious. And in fact, this slide comes from a guy called Dave Corbett at Enron, okay? The most flexible part of any, and I'm talking about electricity, although you see I'll talk about other parts of energy vectors. The most flexible piece of technology and the most flexible thing in any power system that we know of is this. It is the cheapest, the most reliable, and by far and away, in any economic analysis, the best form of flexibility we have. There is no competition to it. None. Zero. There's nothing comes close to it. Okay? Nothing. So it's a funny slide, but nonetheless, it's dead serious. Okay. And the reason why is that, for example, this is the IPCC report that was part of this. If you have transmission, okay, this idea that the wind comes and the sun comes and it's sort of up and down, etc. If you aggregate or average this over a large footprint, what happens is these changes become less. You average it, yeah? So if you take any sort of noisy process and average it, it gets smoother. So in fact, the need for flexibility. So first of all, transmission reduces the need for the flexibility to start with. So it actually concentrates by simply saying the amount of flexibility you get is reduced. If you look at solar, it's similar. The reason I show this slide is because I come from a country with lots of wind, very little sun, but I always show it applies to solar too. This is a slide from a colleague of mine in VTT, Johan Kivinuma.
So they did an analysis of it, and it's comparing flexibility options. And very simply, if you look at it, you know, transmission is the best cost benefit. Power to heat, in other words, so transmission is number one. Power to heat, in other words, if you integrate the power system with the heat system, you get flexibility. It's pretty cheap. The next one is demand response, and the next one is battery storage. I'll actually talk about all three of those. I won't talk about storage, okay? So he did this analysis. So, does anyone ever meet this gentleman here? There was a film about him recently, wasn't there? Who does he look like? He looks like Abraham Lincoln, doesn't he? Okay, his name is actually James Charles Smith. He goes by the name of Charlie Smith. The reason he goes by the name of Charlie Smith is because James Smith is far too common. He was on the US terrorist watch list simply because his name James Smith was too common. That's not a joke. He was on the US terrorist watch list because his name was James Smith. And he wasn't allowed to fly several times because of it, okay? Okay, so Charlie Smith, a very good friend of mine, he runs the Utility Wind Interface Group in the US, which is a group, he runs a group of industries who are trying to integrate all the nodes into the system. And Charlie has made this statement: if you love wind or solar, you have to at least like transmission, okay? But then enter the consumer. Now I put consumer, I don't care. Look, I'm an engineer. Consumer, citizen, they're all the same. People, I don't know. I'm sure there's some definitions that I don't know about. This is a quote of a friend of mine, Yanis Bialik, who was at the University of Durham. He's now in Smalltech in Moscow. And he says, engineers and economists tend to be ignorant and argue about customers. Yanis Bialik, okay? Now, actually, this is one of your colleagues, I don't think he's here. A more formal definition that appeared in a journal. You know, someone pointed out to me that, look, there's actually I was using this as a personal reference. Someone said it was a real reference, okay? So, but I think you get the point, don't you? So in enters the consumer or whoever they are and says, oh, I don't like the transmission, I don't like the wind towers, blah, 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 etc. So electrical transmission is almost certainly the most cost-effective technology to enable integration with manage society inside the objectives. So social science research to minimize opposition. Okay, let's go back to this. One of the ways you can do this as well is to say, well, what about if we alter the demand side? What if we, you know, when we've got too little wind and sun, we reduce the demand, and et cetera, et cetera. So it's demand response. I'm sure you people know a lot about that. If you go and look at demand response though, okay, and I just put this in as a little, you know, even demand response, smart meters are not healthy for children and other living things, okay? So there's even opposition to them, I'm sure you know about it. But that's a side issue for this. What I'm trying, sorry, this is my view of social scientists, I don't know. A bunch of lunatics hanging off a tree. But if you look at the business model, and if you look at the economics, and you look at the systems, and you look at the money and all the rest of it, the simple fact of the matter is that demand response, in large part, not always, but in large part, is a very, very difficult, time-consuming thing to do for very little reward. So I put the 2 pints of Guinness. Everyone knows. Anyone here never hear of Guinness? Good. So the export market is doing well. The analogy I give you is that if you gave complete and total control of your electricity, you know, to TSO or DSO or the system operator, and said, yeah, sure, you can turn on and off my stuff or whatever, and I've got certain constraints or whatever, you might get 2 pints of Guinness every month. You might. Like, there's not enough money in it. It just doesn't, you know, just doesn't stack up. Okay. This is another example of this. Is that, and again, this is preliminary results. There's actually better results than this. They're actually much more. They're actually going out in a journal paper, but this is easier to explain. So this is not a scientific result. It's an illustrative. There's a thing called effective load carrying capability on a power system. Okay, it's a reliability metric, if you want. The demand response can contribute to it. Okay, demand response can actually have an impact on the reliability of the power system. But the important point of this, about this slide, is that this is electric thermal storage heaters in people's houses, right? Helping the entire power system to be reliable. So I go back to my integrated energy system. This is the consumer in their house with their storage heater, all the way up to the transmission system operator across the whole scale. So back to that point, okay? And that's a direct connection between the power system and the customer. But from the point of view of the social sciences, this characteristic is different for different types of people, because they have different profiles of how they live, etc., etc., etc. Okay, this is probably one of my best, well, I keep on saying I must change it sometime and update it, but I never do, and I keep on explaining it. So maybe when I'm 70, I'll keep on using the same slide. I'm 40 years away from 70, actually, just to be clear. Martha, is that right? Okay, so let me try explain this as best I can. So if you take, so what, the red and blue line, the blue line is the load in Ireland, electricity load averaged over the month. And as you can see, we have a system that requires more electricity in the winter than the summer. We're a winter peaking system. Okay? The red line is the wind in 2010 in Ireland, the wind power production in Ireland, over the period of the year, average per month. But we didn't have that much wind in the system. I simply, as a good engineer, I scaled it up by a number to make sure that the amount of energy is the same as the amount we need over the whole year. Okay? So in other words, if someone said to me, Mark, we're going to run the entire system off wind. Now, this is a thought experiment. I'm not saying that's what you should do, but there's all sorts of reasons why you wouldn't do it, and there's all sorts of better technical solutions about mixing wind and solar. But it's a bookend, okay? It's an extreme example, okay? So someone said, I want you to run the entire power system off wind in Ireland, okay? You would do this analysis not only on a monthly basis, but on a weekly, daily, hourly basis. There's lots of other dimensions to this analysis that you have to do. But just as an example, if you say, on a monthly basis, can you do it? And we'll forget about losses, just a very simple example, okay? If you look at it, right, you'd say to yourself, well, you know, it turns out in Ireland that in fact it's extremely windy during the winter and not so windy during the summer. So in Ireland has an advantage that the wind tends to be there during the winter when we have higher load. So that's good. But actually, there's just too much of it. And there's too little in the summer. So in fact, you know, our profile is reasonable in shape, but actually in absolute terms not great. So someone might say to me, oh sure, we'll do demand response. Yeah? What are you going to do? Charge up your car in the winter and drive it all summer? It's ridiculous. It's insane. It doesn't make any sense. If someone goes and says, well look, this is the excess energy, this is the shortage, why don't you store it from summer to winter, or from winter to summer? Sure. We have one pump storage station in Ireland. It's 300 megawatts, it lasts for 6 hours. How long would that supply energy to the entire power system of Ireland? 20 minutes. We need 5,000 of them. There might be 2 other sites in the country that are suitable. Okay? So, demand response and storage do not make sense at all. Now, again, if we go down at different levels of granularity, you get different answers and those other things. But my point is, demand response and storage simply cannot come close to this. However, maybe if we decided to change how we live, we might be able to do this. So, for example, we might decide that during the winter, we will have manufacturing facilities that use a lot of energy producing widget A. But during the summer, the same manufacturing facilities use very little energy to produce widget B. So in other words, you might actually plan society around these profiles. And in fact, demand response, in my opinion, will be huge, but not because of these things or these things, but because of how you plan your energy system and how you live now for 30 years' time. It's a long-term play. Because at the moment, the demand response it's not fit for purpose. But if you design it in advance, it might be. And let me give you an example of that. This is China. China, how do they do it in China? Now, China has enormous problems integrating renewables, and I won't go into what they are, but a lot of them are political and regulatory or whatever, but they have enormous problems. They dump enormous amounts of renewable energy. This is their solution. This is centralized thermal storage. This is a building. This is actually, I keep on having to change it. 500 meters, 500,000 meters cubed. I never change it. I'll keep on, it's one of those jokes I just keep for the rest of my life. We're talking about these things in a house, this size, yeah? Okay? And the Chinese are looking at these things, the size of the building, yeah? And the difference economically is, storage at this scale is infinitely cheaper. Infinitely cheaper. Because the surface area of the insulation, I won't go into technically, but the surface area of the insulation is R cubed to R squared or linear. So in fact, this form of thermal storage is enormously cheaper than this form. But remember, in Western Europe, or at least in Ireland, people like to have their own heating system, their own, yeah? And if someone said, well, why don't we increase the size of these things to make it bigger? Sure, build an extra room in your house for the thermal storage heating. It's insane, it doesn't work. So my point is, the way the Chinese live in extremely large, high-rise buildings, is more suitable for this than an individual heater. So it makes the point. How you live can determine how you do this. Okay? And this is the technical results of the study that we did with the guys in Qing were all about it. And basically it showed you that in China, thermal storage might actually make a lot of sense. So flexibility demand is a cost-effective technology. The financial rewards to the consumer are questionable. But I think the most important thing is this. We may have to change how we live. Okay? I think that's the important thing. These are some observations. I don't tend to rant, okay? There's a lady there in blonde hair and she's laughing her head off me. I won't pick on you, right? No. So these are some observations. They're rants, okay? I'll put them into the... I will admit that they are rants, okay? For this I was very objective, wasn't I? I've no idea what this slide is about, actually. The reason I have it in there is the last time I gave a talk similar to this, I had this slide, and I kept on wondering, why do I have this slide? And I can't remember, okay? So, but I think what it has to do with is engineers. That's a great view of an engineer, isn't it? Hard hat, shovel, gun. These are the social scientists hanging off the tree. This is industry. And I think what I'm trying to say here is that, look, this is engineers, social scientists working with the industry is a good idea. I think that's what it is, but I'm not quite sure why that. This is another rant, a few little diagrams I think are very important. Research funding, right? You all recognize this. You get the funding, the academic or the lead PI gets the money. Who takes it first? Goddamn university. Who agrees with that? Bureaucrat with that. Administrator, are you? Are you university administrator? No. Why'd you put your hand up? I agree. No, but I said who agrees with it. You disagree with it. Okay, sorry. Okay, but anyway, the point is that it goes through all these things in here. Okay, I think myself, and this is, I get into trouble for this, but I'll say it again, I don't mind getting into trouble. My fundamental belief is, and I'm on record with this on YouTube and everything saying this, is that, I'll be careful how I say this. I believe, myself personally, that we are wasting enormous amounts of funding of research in absolutely rubbish engineering research. Tons of it. Lots of Me Too stuff. Reinventing the wheel, redoing it, and it's garbage. It is absolute rubbish. Now, I'm not saying we shouldn't invest in engineering research. We should. But for God's sake, at least fund stuff that matters. But we seem to have this view that, oh, we have this problem in the energy system, pump loads of money into engineering research and energy and it'll all be solved. I don't think that's true. I think that's untrue. I actually believe we should give more money to the social scientists because they're much more important. I believe that. I'm not just saying that so people are going to buy me drinks in the bars. I absolutely fundamentally believe that. The other one here is this one here. Does your laptop keep running out of power, no longer use the natural power of your own laptop? You've seen this before, have you? Yeah? Lots of people in the world believe this stuff, yeah? They do. And this one here is this is probably one of my favorite movies, yeah? 300, yeah? So that's the engineering. So quality over quantity. I don't know why it said quality over quantity, but I found it into it. I think what it's got to do with is these guys are quality, you know, and they beat the, well, they didn't beat them. At the end of the day, the good guys always die, yeah? Nonetheless. So, there you go, beware. Kind of on the social scientists. I think that, I still don't know what, these are slides I had and I said, I'm not sure why I have it. So, I think the point of this slide is that, I don't know, you can see what the point of the slide is. Okay, observation. It's much more about education than research. That guy on the plane, like it's not research to try and educate him or whatever, yeah? I'm the wrong person to educate him. But you know, it's hugely about education of people. So we don't need to do detailed, well, sorry, you need to research how you communicate with them, etc. Research funding is needed, but not necessarily extra research funding. Maybe it should be diverted to other places. Beware the hammer and nail brigade, right? And what I mean by that is there's a bunch of people out there in this area who say, oh, my technological solution will solve everything. Of course they will. They want research money, they want profile, and I can assure you 90% of it is a waste of that. 80% is a waste of that. But it's very difficult to encourage research in technology and social sciences in the universities. It's a pity the rector is gone, right? My experience in universities is the following, is that if you go into interdisciplinary research, right, and work with colleagues in engineering or you work cross-discipline, what you find is, first of all, you find it difficult to get your paper published because one journal says it's not engineering, the other journal says it's not social science. When it comes to tenure, you know, the tenure track system in the US, people look at it and say, oh, you don't have your 10K, you don't have this, that, and the other, because you're in an area that sort of falls between stools. Am I running short of time? Are you sure? Am I okay? I have to do as Martin tells me. Okay, that's that. So the international context, so I'll be very quick about this. So this is the set plan, the new sort of upgraded set plan. I'm sure our colleague can tell us about it, he might have written part of it. If you look at this document and download it, and if you read it, now my interpretation of the document, you can take your own, is there's two key things in that document that stand out to me. The importance of the consumer and the importance of the system as one integrated system. So both topics I've spoken about, okay? This is the Energy Systems Integration Facility at NREL in the United States. It's a 135,000 square foot purpose-built building to do integrated energy systems at a cost of $150 million US. Okay? This is the catapulted energy system. So I'm trying to make the point here that internationally this whole concept of the integrated energy system is coming to the fore and the consumer is front and center of it. This is an organization that I lead. This is the International Institute of Energy Systems Integration. We are trying to reach out to, we admit it, we're all engineers, we started, but we do want to work with social scientists, etc. I'm here to talk to people about it. So these are the organizations that are in it, Period, NREL, KI New York, EMRI, GTU, KU Movement, myself and Brian lead it, and you can check out our website. And in fact, that's the first place I met this gorgeous young lady. There you go. My wife, I want to know my wife. So we had a meeting in Imperial College London in March. Martha turned up to us, and this is, and in fact Sarah was at it too, but I highlight this. This is the important. For example, I don't know if this makes sense. For example, the difference between electricity and heat for an engineer is as profound as the difference between consumer and citizen for social scientists. So to an engineer, electricity and heat, two different things. To an engineer, customer, citizen, same thing. But I'm sure it's not. But this is understood as one of the significant outcomes. We need to combine economic, social, and political perspective of engineering. That's an outcome of our work. This is another organization. This is the joint program in ERA. So the European Energy Research Alliance has these joint programs. This is one in energy system integration, and I lead it, so that's another initiative internationally. This is our work program, and you can see consumers in there. And this is what's happening close to home. This lady here, I think, is familiar to some of you. I don't think she's here. She works in my university, and she's involved in a very large research program that we have in integrated energy systems. So she's a social scientist. We're looking at integrated energy systems. She's participating. So conclusion, it's more about the whole integrated energy system than ever before. Social science is incredibly important in it. But this, scope, funding, quality, and leadership, all important. The leadership in the university systems, the researchers, and the funding agencies, I think, is missing. They need to lead. They need to deliberately go and fund this work, despite the fact that the system may not, reward, etc. They need to force them. Plenty of activity going on, and how to coordinate it all to get the best impact. Okay? But my last slide is this. People talk about trilemma, yeah? I don't know what the word is for a four-lemma, but what the hell. They talk about, sustainability, security. Who's this gentleman? Well, maybe he's not a gentleman. Security, supply, sustainability. This is to represent economy, whatever, right? I believe it's actually a four-lemma, whatever. I think the one part of it that's missing is this. So I'd like to thank Mark in particular and Professor Gordon, our Martin, for behaviour to provide me. Linda Stegg will be here tomorrow. She's a person who sort of introduced me to this area. I've spoken to her, I've learned a lot from her, etc. She's involved in a lot of things. And I've stolen most of my slides from my colleagues. Thank you.